We are almost done with the whole semester. Section 11.6 on the binomial theorem is our last section of the semester. And the binomial theorem is a neat shortcut trick for answering questions like the one on the whiteboard. What are the first three terms of the expansion x plus y to the 10th? And if we really need to answer this question, we definitely would like to have a shortcut, because right now my only technique for being able to figure that answer out is to actually just brute force multiply this out. So I would have to do like x plus y times x plus y. I'd have to multiply that all out, first, outer, inner, last. That would give me x plus y squared. But then I'd have to do this x plus y cubed after I was done with that. And then at the end of the day, after a long time, I would get to the 10th one, and I probably would have made about 65 different algebraic mistakes along the way. So our goal in this video is to figure out, is there a pattern when we go from the square to the cube to the fourth to the fifth that we can use to predict what this answer would be without having to go through the slog of actually multiplying it out? So we're going to start small. X plus y to the 0 is equal to 1 because anything to the 0 is equal to 1. X plus y to the first is equal to x plus y. That's not hard. Okay, so here we have to do a little bit of work, right? X plus y squared. Let's actually figure out what this one is. Like I said, we'd have to multiply this out. And we have to remember to multiply all the terms together. So my first terms give me x squared. My outer terms give me x times y. Inner terms give me y times x. And y times y gives you y squared. And then we recognize that these two terms in the middle are actually the same thing. X times y is y times x. And we're going to get x squared plus 2xy plus y squared. On the next slide, we're going to write down what you get when you get x plus y to the third power. So I would have to take what I just got, x squared plus 2xy plus y squared, and multiply it by another x plus y, where I made sure that every term got multiplied by x and every term got multiplied by y. I'm going to skip to the punchline for us. If you do that, you get x cubed plus 3x squared y plus 3xy squared plus y cubed. If we do this to the fourth power, you get this. And if you do it to the fifth power, you get that. So I multiplied out these bigger binomial expansions for you because this video is not about practicing our skills of multiplying out huge binomial expansions, but rather trying to find a shortcut for that so that we don't have to multiply out huge binomial expansions. And there are lots of patterns to find here. You probably already see a few. The first one I want to note is how many terms we have. So notice that when I had x plus y cubed, for example, I had 1, 2, 3, 4 terms. And x plus y to the fourth, I had 5 terms. X plus y to the fifth, I've got 6 terms. So let's write this down. We can notice that when I have x plus y to the nth power, we're going to predict that we're going to have one more term in the expansion than we have in the exponent. So we're going to have n plus 1 terms. All right, you might also have noticed that each one of the expansions start off with x to whatever power we're on, right? X plus y squared, cubed, fourth, fifth. We always start off with x to whatever power we're on. We also end with y to whatever power we're on, right? Y squared, y cubed, y to the fourth, y to the fifth. So we would expect when we multiply out x plus y to some integer power to the n, we're going to start with x to the n, and we're going to end with y to the n. The next thing we're going to notice is what's happening to the x and y exponents in the expansion. So let's just look at x plus y to the fifth because it's got more terms to notice. We start off with x to the fifth, but then after x to the fifth, the x exponents are going down by 1 in each term. 4, 3, 2, x to the first. Even the last term you could think of as having an x to the 0th power. X to the 0 would be 1. The y's, on the other hand, are increasing. We start off with y to the 0, then we get y to the 1, y squared, y cubed, y fourth, y to the fifth. All right, so the x powers are decreasing by 1 in each term. So the powers of x decreases by 1 in each term. The power of y increases by 1. You might also notice the relationship between the exponents on the x and the y. So in each pair of terms, let's look here. So this fourth and 1, the 3 and the 2, 2 and the 3, 1 and the 4. Those always add up to 5 in the x plus y to the 5th expansion. It works in the x plus y to the 4th expansion as well. 3 plus 1, 2 plus 2, 1 plus 3. The x power and the y power always add up to whatever exponent you're on. Okay. So the exponents of x and y in each term sum to n. So it seems like we can totally predict what's going on with the x's and the y's. The only thing we haven't talked about is those coefficients. So in the x plus y to the 5th, the 1, 5, 10, 10, 5, 1 coefficients that are stuck on each term, how do we predict those? The only thing we could probably notice on this slide is that these coefficients are symmetric. So if I look, I've got a 1 here, 5, 10, 10, 5, 1. They're kind of mirror images of each other. And that's actually true for all of the expansions. In the x plus y to the 4th, you've got 1, 4, 6, 4, 1. In the cube, 1, 3, 3, 1. And in the square, 1, 2, 1. So the coefficients are symmetric. Okay, so they're symmetric, but how do we predict what they're going to be? We're going to get those symmetric coefficients from something called Pascal's triangle. So let me show you how to build a Pascal's triangle. It's a triangle of numbers, and it starts off at the top with a triangle of 3 ones. So you're going to build 1, 1, 1. And then each row of Pascal's triangle is going to start off with a 1. And then the numbers as you go left to right across are just going to be the sum of the two numbers above it. So those 2 ones here, I'm going to add those together to get 2, and that's my second number on the next row of Pascal's triangle. And when you run out of numbers to add, you end the row with a 1. So on the next row, I'm going to have 1. I'm going to add 1 plus 2 to get 3. And then 2 plus 1, I'm going to add to get 3. And then we end the row with a 1. All right, so you can keep building this as long as you want to or need to. Start the row with a 1. 1 plus 3 gives me 4. 3 plus 3 gives me 6. 3 plus 1 gives me 4. End the row with a 1. And then my next row, I can add 1 plus 4. And we can keep building this as long as we want to. All right, and if you take these coefficients, these numbers in Pascal's triangle, you can go back and look, and these are exactly the coefficients that show up on the binomial expansions on the previous slide. And if you line them up, you'll see that this is the row that belonged to x plus y to the 5th. This is the row that belongs to x plus y to the 4th. So you can see the row starts off with 1, 4, 1, 5. You just find the row that has the exponent that you're looking for. The only trouble with Pascal's triangle is if I ask you to multiply out x plus y to the 10th, you have to build up to the 110 row on Pascal's triangle, and the numbers can get kind of big. But other than that, it's a really easy trick.